So hello everyone. Hopefully you enjoy all the talks from today. I'm Miro from Argonne National Lab from the Computer Science Division, a Computational Science Division. I also work for the Leadership Computing Facility. So today I will talk about how we get QMCpack ready to model material for exascale machines. So first acknowledgement. So the work is funded by the Exascale computing project. We are an application development project. For this reason, so here's our team. The project is led by Paul Kent. Probably a lot of people, he's from UK, so a lot of people are familiar with him. So we are working for the exascale systems, but there's no such machine still for production today. So mostly we are working, instead of on the right side, most on the left side. These are machines on the floor. So we just want to be sure that when we pull the code, all the machines are covered with GPUs from NVIDIA, from AMD, and Intel. But the major focus of today's talk is, as we pull the code, is mainly on NVIDIA GPUs. So that's my focus. So here's the simple spectrum of the electron extraction method. From quantum chemistry methods, very expensive, high ordering, high scaling, with a number of electrons or orbitals. Then QMC is kind of in the middle. And a lot of audience today is from DFT, which is cheaper than QMC. Even you do the most expensive, like hybrid functional, it's still much cheaper than QMC. On the other hand, QMCs can scale very well over the whole supercomputers. So it has its own appealing point. So on today's petascale machines, my experience with QMC is I can do a system with roughly thousands, a few hundred to 1,000 electrons comfortably. So what's next? We would go for exascales. We clearly want to go much larger problem sizes. So the target is to make sure 1,000 atoms in the simulation works roughly with 10K electrons, since we use pseudo potentials. On the other hand, this is just part of the goal, because not everyone runs those heroic simulations. People still daily run small systems with maybe 20 atoms or 100 atoms. So we want the code to be efficient across the whole spectrum. So QMCpack is the code I work on to implement the quantum Monte Carlo method. So we have both the real space method, like variational Monte Carlo, diffusion Monte Carlo. Well, we also have second quantization orbital space method, like auxiliary field method, quantum Monte Carlo. So, but what I will cover today is mostly the real space one. So in the real space code, we used to have C++ is our language. Then we adopt the MPI plus X programming model. So by the name, it's quantum Monte Carlo. So Monte Carlo actually indicates it a lot of many Markov chains advance in parallel. So in QMC terminology, we call it walkers. Then it mentions quantum, means it's we are solving a many-body problem. So actually many-body electron problem. So these two characteristics bring us the concurrency in the code. And to have a efficient porting is basically mapping those concurrency onto the actual hardware we target to run. So give you some ideas about the diffusion Monte Carlo algorithm. So schematically, yeah, you basically have a population of walkers. You start from electron positions, and over time, you move random walking those electrons, you compute some properties. Their weights dynamically changes, and you have to do some load balance at certain point. But the bulky calculation is during the random walking and the evaluation of observables. So the load balance and communication is very light. So how to map those concurrencies? So the high level, the worker-based worker concurrency. So basically, we just divide the population in over MPI ranks. Then each MPI rank, the communication between them is pretty light in general Monte Carlo code. So we achieved very well scaling over the whole machine. Like Mira, it has like 32,000 nodes. It's not a problem. Or Summit on Titan, the old machine, it's 95%. We are just doing 1 MPI per GPU. So high level decomposition of the problem, no problem, it brings some very good scaling on all the supercomputers for machine level. Now it becomes down to the lower granularity. So we still have a bunch of workers to be advanced, either on a CPU socket or on a GPU. Yes, we still have some worker level concurrency. Now it's not a good thing. Actually, it becomes a challenge because workers are not data parallel. They are task parallel. Because of random walking, some workers get accepted. You need to do some computation. Some worker gets rejected. It doesn't do some computation. There's this behavior divergence. It's not a problem for CPU, but it becomes a challenge for GPU. Because GPU wants to do the same task when you offload the kernel to the GPU. So worker parallelism is a challenge. Then the lower level, electron parallelism. So as I mentioned, we are nowadays comfortably running hundreds to thousands of electrons. So they are actually, you do calculations of orbitals or pair potentials. They're very well vectorized for the both CPU SIMD and GPU SIMD architecture. So it's not a problem. However, if you think about kernels, if you just do one worker, think about 1,000 electrons, it's actually a too large number for CPUs, because if you multiply the number of cores to the number of SIMD lanes, it's roughly still just a few hundred to a few thousand. So a few thousand is already kind of stretching the CPU limit. However, if you think about GPU thread, 1,000 is really, really small. So it's not efficient for GPUs. So to have efficient GPU calculation, we need to combine both the workers and the electrons to have enough concurrency for each GPU kernel to be efficient using the GPU. So as I explained, we have to solve the problem of number of electrons, this degree of freedom, as well as workers. So we really want a QMC algorithm which implements a QMC equator driver to be very efficient in these brown areas. However, the reality is the existing implementation in QMCpack has a existing implementation have its own limitations, and it's cornered in a specific area in this problem space. And we really want to address that. So the issues of classic QMC drivers, the classic drivers does one worker each operation at one worker time. It is fully asynchronous. It's divergent behaviors across all the workers. So it's not friendly for GPU computing at all. So we cannot start from that code path to do GPU offload to GPU computing. The existing, we call it legacy CUDA implementation in QMCpack. That was a CUDA implementation added 10 years ago in QMCpack. It still works fine, very performant. However, it hits certain limits. So the reason it's efficient is all the workers advance in lockstep. Lockstep means that they do all the workers do exception. Even some workers doesn't do the work, you can ignore them. So you make sure there are enough workers sent to the GPU to saturate the card. So kernels are heavy, it's good for GPUs. But on the other hand, this 10-year-old legacy code only launch GPU kernels from one CPU thread. Regardless how many cores you are available for the NPR rank, they can't submit jobs to the GPUs. So when you are doing small simulations, GPU cannot be saturated, and you have to rely on multiple MPI token tools the same GPU. This is just a different level of complexity, and we really want to avoid that. So on the other hand, the legacy CUDA code made a choice that all the workers must be executed together. Somehow it restricts its efficiency to the smaller smaller problems that, it relies on high worker count to be efficient. In the scenario, you are doing challenge simulations because of memory limit. So your worker count becomes low and you can't be efficient. You will see the difference why legacy CUDA is bad. I will show you later. So another key problem is this code is not maintainable and not feature complete, because somehow over the classic CPU driver and legacy CUDA implementation are added independently. They don't crosstalk, means you have to implement feature twice for the CPU and for the GPU, for the CUDA code. That is not workable. So what we do is redesign the application. It's computational pattern. So we no more just, in the new design, we divide the worker population into crowds. Crowds is not a physical concept, but actually to help the computation in GPU. So somehow with this new design, when we put a large crowd size, it has all the benefits of the legacy CUDA implementation, that behavior. You can do lockstep computation. You have efficient kernels. And because now we have multiple crowds, we can actually have multiple host OpenMP threads talking to the same GPU. So once if the GPU, so these threads kind of try to submit kernels large enough to the GPU, and GPU will be kind of nonstop servicing those compute requests from those threads. So you think about a node architecture, you have many cores, you have many GPUs, all the resources will be used by QMCpack. This design by itself doesn't care anything about CPU, GPU. It is fully agnostic at this level. And we also added a way to allow batch the APIs added to fall back to existing CPU implementation. So it becomes fully feature complete. So lessons learned so far. We really need to understand how to make CPU and GPU compute efficiently. Then what we need to do is analyze the code compute pattern and make sure you have the mapping from the existing concurrency to the parallelism properly. By doing that means you know that when you start at the every entry point you need to do GPU porting, you're guaranteed to have enough work and you're guaranteed to have minimum data transfer needed. So the next step for what we need to do is to sketch a porting strategy. And we start with some experiments. So about GPU porting. So what we do is, so I mentioned we have the legacy CUDA code, which is fully CUDA C++ kernels. What we do now is instead using OpenMP offload for kernels. And we also call the vendor libraries. So Kublas, Solver, come with it. We still need a bit of CUDA just to smooth out all the interactions. But somehow we minimize the use of CUDA kernel language. So on the OpenMP also, we use its CPU threads. So we kind of have a nested architecture. So we have OpenP threads on CPUs, and each of them do OpenP target offload. So this is the overall design. And we first experiment whether that OpenP runtime can actually saturate the GPU. So this is a study on mini QMC, which is a mini app. And we just found all the threads and let them launch kernels. And in the implementation, in good OpenP runtime, offload runtime implementation, each offload will pick up a CUDA stream. So somehow you have independent CUDA streams, and those kernels can happen concurrently. And the GPU gets saturated. In addition, because when you do OpenP offload, you transfer data, you launch the kernel, you transfer data back. So somehow this is on one stream. Then you have another offload region, happens the same operations. And because so because of the independent streams, you will see those. I'm sorry. You will see those concurrent things happening. Okay. So including concurrent execution and overlapping data transfer and execution. So here's the performance after we finish the porting on Summit. Okay. As we port, so we started the actual porting in 2019, and over a few versions, we see the performance improves. And now the OpenP code has a performance close to the legacy CUDA implementation. So we achieved the performance goal. For the largest problem size, we adopt some algorithm changes, and you see that the new code clearly wins. And works very well across problem sizes. So this is the lessons learned we learned so far. So OpenP plus vendor library does work. And we need much fewer CUDA kernels and offload regions. It is maintainable and with decent performance. Oh gosh. The last part. So data movement is the key for porting. So similar to MPI, interconnect is slower than memory. We learned how to program MPI properly. So with the memory and versus cache, we implement cache-friendly algorithms. GPU bus is similar, and we deal with it with proper data transfer management. So this is the top priority for me to consider when porting to GPUs. So writing kernel is very simple. It doesn't need expert knowledge, but manage data movement requires you to be the domain expert managing this algorithm and implementation. You have to think about a few more levels of parallelism in your code to fully utilize all the resources. So you need at least 2 levels. And in QMCpack, I've shown that we actually have kind of 3 levels. We do a lot of reductions in HPC code, and that means you can't avoid thinking about locality and hierarchy in those parallelism. And also, CUDA C or Fortran language writing kernel is not the optimal choice for scientists. They have to be protected under macro. They add a lot of test burdens. It doesn't run on a host without GPU. So running debugging on the host usually is a lot smoother and catch most user errors. And host side tooling are much better. We have address, thread, sanitizer. We can run code coverage. So for me, offload models are more appealing. OpenACC or OpenP, both are in this category. We should restrict using CUDA, a programming language, only to servicing around those vendor library calls. Scientists should spend time on methods, algorithms, leave those engineers to worry about absolute for performance. If not using CUDA brings you 20% loss of performance, ask those 20% more hours to the compute centers. A bit about OpenCC versus OpenP. They are both competitors. They're somehow kind of relatives. OpenP has a richer feature set, but OpenACC is more developed for NVIDIA GPUs. So somehow the good part is the needed developers mentality is the same for both programming models. So even switching from one to other when you need to do that, it's a lot easier than switching from a CUDA kernel language to offload. Unfortunately, they are not necessarily interchangeable in syntax. So choose one based on your production environment and programming language. So the situation for C and Fortran is not equally the same situation, the status. Keep in mind, compilers are never perfect. They are written by humans, they have bugs. But be kind to developers, especially because directive-based programming models ease the burden of code developers and shift that challenge to the compiler developers. So try to work with them to ensure all your needed features can be implemented and optimized. Remember, CUDA doesn't have a reduction. I think Stefan also mentioned, scientific code reduction is extremely important, and writing reduction is a challenge. It's never an easy task. Okay, so here's my summary. So after we carefully redesign QMCpack, we make sure that the code architecture serves well both CPU and GPU. And we did our second GPU porting on top of it. Our OpenP plus vendor library strategy works very well on NVIDIA GPUs. And we are expanding the list of support GPUs from different vendors based on this design. So my word, GPU porting is a chance to force designing, implementing better code. Don't miss the opportunity. Thank you.
Thank you very much, Ian. I appreciate it. We are almost on top of the time, so I have a very quick question, and then maybe you can leave on the chat your email address, so if people are more interested into QMC method and GPU and QMC method can reach you out. UK has a, there is Casino. You're familiar with the code. There's a community of QMC people that are very interested to learn from QMCpack experience. So my very short question is the following. So around OpenMP and OpenMP offload in particularly, what's your view, or what have you adopted in QMCpack in terms of standard? Are you still in the OpenMP 4 type of family, or are you moving to OpenMP 5 because it's better, it's more flexible? What's your, what do you use first of all in QMCpack? Also, what's your opinion in this particular topic?
So we started for OpenP 4.5. So it basically have all the foundations, the building blocks we need. However, certain restrictions they put in 4.5 was removed in 5.0, and 5.1, 5.2, they're just refinements. So the original restrictions they put in 4.5 removed in 5.0, my feeling is you basically, how to say, as an OpenMP scientist mindset to think about it, this restriction should not be there. So basically, if you put with a bit of your instinction, your code will be likely work with 5.0 instead of 4.5. So go with 5.0 and you won't have hit major issues.
Mm-hmm. Mm-hmm. Okay, one very quick last question. How do you see the interaction of OpenMP CPU versus OpenMP offload in the same code base?
Because QMC, we use OpenMP threading at the worker level or crowd level, while offload is more a lower level thing, because that becomes a implementation detail, so it should live in the low level thing. So high level use OpenMP threading, low level use OpenMP offload, so they work together. When we are not using GPU, the offload portion is just running on one thread is okay, because the high level threading is already enough to utilize all the cores. And the SIMD, the vector code, offload vector code, as I said, SIMD is the same thing. So the efficiency is good.
Okay.
And indeed, we actually still keep the old pure CPU implementation, and all the features, the GPU, non-GPU features, you can select from input. And also the offload code can be compiled running on CPU, and you can do debugging and all the needed work, even though the performance is not necessarily give you the best performance. But for development, it's super friendly.
Understood. Okay. So thank you. So thank you very much again for being able to join us. And